So that is one thing that we are doing here. See, if you remember, what was our two stated goals which I erased off the board? What are the two stated goals that we had? One was to find some parameters that best explains the data. What was the second goal? Exactly, right. I am doing the best, I am actually finding the best parameter, like one single setting for the parameter that best explains the data that was given to me. That is what we have been doing so far. But in terms of finding the best prediction for a new data point, am I doing the right thing so far? Is it the right way to do it, right? So if you think about it, right. So probability of x tilde given x is the probability of x tilde given theta times the probability of theta given x summed over all theta if theta was a, I mean if it was a discrete probability distribution, but since we have been considering Bernoulli and other things, it is going to be a integral over all theta, right. I am not talking about the outcome, I am talking about the parameterization. So the parameterization is a continuous parameter, right, theta is a continuous parameter. So I can't sum over theta, it is not like I am only considering theta 1, theta 2, theta 3, I am considering theta in the interval 0 to 1, right. So it is integral over theta, right. So this is the actual outcome, right. But think about what happens in the case of the prior or any one of this case, right. I am only picking one theta, it could very well be that there is another theta which also has a high probability of being correct, but since I am picking only one theta I am sticking with that, right. There could be two different thetas which I could have used there, right. In fact I should ideally be using all the thetas, because for a certain parameter setting some x tilde might have a high value, right. So even if that probability of that happening is very small, right, I should still be accounting for that in my prediction. That makes sense why this is a much better predictor than using ML or map. But why do not people use this then? Computationally hard. Why? So far I was actually trying to avoid computing probability of theta given x, right. Here I did that by assuming everything else was constant, right, and I just had to do the likelihood, right. Here I said okay I am just doing a point estimate, so I can ignore the denominator, I can only do the numerator, right. But when I go here, boom, I have to do the full computation, right. This essentially means I need to know p of x, right, and that becomes hard. Yeah, but computing that is actually essentially hard, you have to actually multiply it over all the data points that you have, right. So it becomes a little tricky, right. And what is p of x, by the way? No, yeah, but what is p of x? P of x is the probability of seeing the data, right. What is the probability of seeing the data? You do not know that. I have only given you the data, right. You don't know the distribution from which the data was drawn. That is exactly what you are trying to do. So the theta gives you the distribution over which the data was drawn, right. So what would be p of x? Right. So that is p of x, right. So how do you compute that?
Here we have assumed a Bernoulli distribution, but if in some other case we don't know the distribution, we cannot estimate the parameter.
Good point. So whenever we talk about parameter estimation, right, so you need to have some parameterized form of a function for you to do the estimation of the parameters, right. So if you remember, in the logistic regression it was not Bernoulli, it was the logit function that we were trying to estimate the parameters for. And I also told you when we looked at LDA, I told you we could make a lot of different assumptions about the parameters. In the LDA we made an assumption. What did we assume? It was a Gaussian, right. Anything else? Covariance was the same, right. This is for LDA, right. And at that point I told you could use mixture distributions as well, right. You could use whole bunch of other things. I also said you could use non-parametric techniques, right, but I told you it is a misnomer, it is a misleading name, because non-parametric really means that you can just keep adding parameters and things like that. So that is a very flexible, very powerful modeling paradigm. So you could do parameter estimation for non-parametric methods also, right, where you have to actually figure out how many parameters you need as well. So then the distributions you consider become more and more complex. Okay, now we are looking at very simple forms, right, but the distributions become more complex and the parameter estimation consequently becomes harder, right. So in fact most of machine learning research nowadays is essentially on parameter estimation for all kinds of different things like non-parametric models, how do you do the parameter estimation, things like that. A lot of research is going into that and a lot of powerful models have come out. Let us go back to our Bernoulli case for a minute, right. I have Bernoulli and my prior is a beta distribution, right. Now I can try to do this. So this will be what? That is P of x given theta, right, that is P of theta, P of x given theta, that is P of theta divided by right, that makes sense, right. This just this P of x, right, this is P of rho given x, right. So x is your C is the set of experiments that we were talking about there, right. So P of rho given x is equal to P of x given rho into P of rho divided by P of x, right. So P of x is given by the integral over the entire row space which is 0 to 1, okay, of P of x given rho into P of rho d rho. That is just the base rule I have written up. Okay. So what is one thing you notice here? What is gone here? Our nice convenient logarithms are gone, right? Right, but it does not matter too much. Why? We are not doing any maximization here. We don't have to take the derivative or anything now, right? I am just actually interested in computing this whole functional form again, and I am not interested in taking derivatives and trying to maximize. So it is okay if I don't have logarithms, but it just makes the whole thing more nasty, right? And it turns out this is pretty easy to compute. So I skipped a few steps in between, but you can figure that out. So I wrote out probability of rho given alpha beta, which is essentially this, right, and this product I can write like this as we did earlier, right. We have done both of this before. So what I have left out here is the normalizing function. There should be a 1 by beta function of alpha beta, right, and then I have this integral also, right. It turns out that this whole thing, including that normalizing factor, is actually equivalent to the beta function of n naught plus alpha, I mean n1 plus alpha and n naught plus beta, okay.
What are the rows or P?
What's that? These are P's, these are rows, yeah. If you remember the beta function, right, it is rho power alpha minus 1, 1 minus rho power beta minus 1, and the normalizing factor is a beta function of alpha beta, right. So it is rho power n1 plus alpha minus 1, 1 minus rho power n naught plus beta minus 1, and then there is the beta function of n1 plus alpha, n naught plus alpha. This is actually itself a beta distribution, right. So it is exactly the same beta distribution. So we started off with the beta distribution as the prior over the rho, right, and then we did this computation, and the posterior turned out to be a beta distribution as well. It is very convenient, right. Right, such distributions which allow us to do this are known as conjugate pairs, right, or conjugate distributions. So what are the two distributions we are talking about here? Beta and Bernoulli, right. So the data distribution was Bernoulli, prior distribution was beta, right. If that is the case, then the posterior will also be beta, right. People know the difference between Bernoulli and binomial. What is the difference between Bernoulli and binomial? Single trail is Bernoulli, repeated trails is binomial, right. It turns out that beta is also conjugate prior for binomial, right. Any other famous conjugate pairs that you guys know? So both the data and the prior can be Gaussian. So remember what we mean by the prior distribution, right. So the prior distribution is the distribution over the parameters of the data distribution. When I say Gaussian, that means that, okay, I am assuming my data is coming from a Gaussian, and I am going to assume that the mean of the Gaussian is coming from another Gaussian, right. The probability of the mean is going to be given by another Gaussian. So that is what I mean by a Gaussian prior. Like in the beta Bernoulli prior, I am assuming that the probability of heads is rho, and the prior distribution over rho is a beta distribution, So, when I say Gaussian, I am assuming that the data is coming from a Gaussian distribution and the mean of the Gaussian is coming from another Gaussian distribution. That is what Gaussian is. There is also another very famous so Dirichlet. So people know what multinomial is. What is multinomial? It is a distribution that will describe multiple rolls of a die, for example. Right. Binomial is when you have two outcomes, multinomial is when you have multiple outcomes, right. So the single experiment, single trial version of multinomial is called, not too many people know it, multinomial. Binomial is called Bernoulli, the single trial of a multinomial is called, no, a very unimaginative name, it is called the discrete distribution, okay. So so multiple trials is called the multinomial distribution, and the conjugate prior for it is the Dirichlet distribution, which is nothing but the multidimensional extension of the beta distribution. Okay, so it is like the beta distribution, but it is a multidimensional extension of the beta distribution. Okay, and there are a bunch of others. Okay, so but there are several that are known, and so typically what you do is you look at your data, right? Look at the data and figure out what distribution is a good distribution for the data, right. So for example, coin tossing experiments, we figured out that Bernoulli is good, right. So die rolls, right, we will figure out that multinomial is a good distribution, right? What about text? People typically use multinomial distribution. So you can think of having a very large dimensional die on one word written on each side of it, right. So what is the next word you use? Roll the die, right, that will tell you what is the next word to use, right. So that is no, do not laugh, I mean that is seriously the model that people use for modeling text, they use multinomial distribution. So they assume that each word is generated independent of the previous word. Yeah, sometimes when okay fine, let me not go there. Yeah, so that each word is generated independent of the previous word, and so you can model that as a multinomial distribution, right. So they actually have different names for it. Okay, it's sometimes called the unigram model, right, or also it's called the roughly a bag of words model, right, where the sequence don't matter and each word is generated independently. So many ways of describing the same idea, right, but at the end of it is nothing but using a multinomial. As comical as it sounded, that is what it means, having this huge die and rolling it every time I want to add a word to the document, okay. So that is multinomial, right. So once you have decided what is the distribution that you think is appropriate for modeling the data, then you go and decide on what your prior should be, right. So sometimes the choice of the distribution for modeling the data is driven by not whether there is a conjugate prior is available for the distribution or not, right. So maybe there is a different distribution that is perfect for modeling data, but because there is a very convenient conjugate prior for multinomial, right, people want to use multinomials, right. So like that there are other instances where even though a Gaussian is inappropriate, for example people want to model discrete valued data, right. The Gaussian cannot do discrete values, right, but then coming up with the distributions which allow discrete values and have nice conjugate priors is hard, right. So people just go with Gaussians sometimes, even though it is inappropriate, they use Gaussians because it has a nice conjugate prior. So why are conjugate priors important? Because it is easy to do things in iterative fashion, right, because once I run some data through the beta Bernoulli pair, okay, I am going to end up with a beta distribution over the parameters again. So if I get more data, right, I can just happily just go ahead and do it, right. If every time I run through it I keep getting a different probability distribution, there is no functional form for me to stick these things into, right, then it becomes very hard for me to do this in any tractable fashion. right? I can't come up with some parameter update equations or anything like that, so it becomes very hard. So, so the conjugacy is very important.